Yes. So so that was off record, right? So so as we'll see, it's very easy to alter band structure, and one can do it preserving high mobility, which is always, often a problem on other materials. And then one can also vary by using gate tunability. One can vary Fermi energy in a really wide range with very modest gating, and so one can do spectroscopy of Berry space basically across the entire Bloch band. So that's the plan. And maybe, so this is what we discussed already. There is no Berry's curvature in graphene, even in pristine graphene, even though there is Berry's phase. The Berry's phase is a pi independent of your trajectory as long as it's encloses direct point. So you can think of Berry's curvature as a delta function sitting in the direct point. If you do it carefully and work out how Berry's vector potential is distributed in Brillouin zone, you will see that it has zero vorticity everywhere away from direct point, and then there is a non-zero vorticity quantized to pi for all loops enclosing direct point, and so that's the. Yep.
Is it okay to speak of Berry curvature for graphene as it's not an insulator? Because we define Berry curvature for insulators, like.
Yeah. So sure. Thank you. Yeah. So yes. So this is exactly why I'm not trying to get. There was a question yesterday. Can you use this delta function and get something out of it? The answer is precisely what you said. We have Berry's curvature defined for insulator, meaning everywhere in K-space where there is a gap separating my band from other bands, I have everything we discussed yesterday. I have Berry's curvature, anomalous velocity, and transport phenomena associated with it. Unfortunately, in pristine graphene, the point where something interesting potentially may happen is precisely where bands cross. So there is nothing interesting from that point of view in here, unless we open band gap. And then if we open band gap, then this basically this delta function curvature broadens into a peak and into a bell-shaped distribution, and you create two pockets of Berry's curvature in the upper and lower branches of gapped Dirac spectrum. And if you do the analysis using closed loops, and it's very easy to do using the spin analogy, because the graphene Hamiltonian looks like Zeeman coupling between pseudospin and effective magnetic field, some components of which are proportional to momenta, and the component responsible for gap opening in the z direction is proportional to the size of the gap. So if you do that, you'll find that depending on your loop size, you get as loop size increases, you enclose larger and larger solid angle, and you get that type of picture showing how solid angle swept by effective magnetic field changes as a function of the size of the loop. So it becomes nice. The question is how to, and it passes your test. We have Berry's curvature and gap at the same time, so we should be able to see some interesting transport behavior. The question is how we achieve that, and so that's where graphene being nice more than one way comes very handy. This bit will be a recent work which is ongoing now. So I would like to acknowledge all the collaborators: Justin Song, graduate student at MIT, Paul Nopsumutraput, undergraduate, and then experimental collaboration in Manchester and theoretical collaboration in Exeter. And these are the papers. So how do we open band gap? We need to create perturbation to open the band gap. Turns out that these atomically thin materials that we introduced yesterday can be combined in a very convenient way to do that. In particular, if you take graphene and HBN, hexagonal boron nitride, and remember we discussed yesterday they have identical structure and they have nearly identical periodicities. So I mean the lattice constants differ by about 2%. So if you put them on top of each other, they come nearly in register, and despite nearly identical atomic structure, they have very different electronic structure, because in boron nitride, B and N sit on different sublattices, and so when they are placed on top of graphene, they create a very strong AB sublattice modulation in graphene, right? So that's very nice, and we can produce the modulation that may open band gap in graphene. Experimentally, this is done in the same way, essentially in the same way as graphene itself and boron nitride itself is obtained at single layer. Peel off single layers using Scotch tape technique that you've probably heard about, and then you just place one layer on top of each other layer, trying to make crystal axis aligned. Then you get the right type of alignment and nearly in register arrangement. And so then that's all. It's very easy. You don't need to do anything really sophisticated. There is interesting material science involved in this, because it turns out that, I mean, you would expect naively that even if you put two layers on top of each other, there will be a lot of dirt accumulated when those layers have been peeled off. Imagine a Scotch tape, remnants, and then all kinds of hydrocarbons. Someone sneezed, and all covered in fairly thick layer of dirt. However, when you put them next to each other, there are van der Waals forces that start working, and these layers get coupled by van der Waals forces, and then what happens is very interesting. All the dirt it aggregates into small droplets, and then these droplets coalesce and form bubbles, or balloons as some people call them, and a large area of the material becomes dirt-free. So because of this van der Waals bonding, you get, it's not a chemical bonding, so structure remains intact, but van der Waals bonding turns out to be strong enough to produce atomically clean areas of many microns in size, and so one can then look at it, and it takes about an hour for the self-cleaning magic to work, and then you can look in a microscope, take the area which is free of those bubbles or balloons, and then make a device out of it. So that's basically how it's done. And so this technique apparently can be generalized. And there is this notion of a Lego type assembly that is pictured here, coming from this paper. It works best so far for this pair of materials, but there are already reports that other two-dimensional crystals can be nice in a similar way.
Excuse me?
Yep.
This kind of modulation will open a gap of mass term. If it is the case, then what's the difference with using nitroboronite?
Oh yeah, thank you. Yeah, so boron nitride is an insulator with a huge band gap, 6 electron volts. So that would be hard to gate even with these techniques, because there's no, people can apply 1 volt, can induce 1 volt Fermi energy shift, but perhaps not more than that. So boron nitride is not a conductor even under gating. I mean, maybe it may change later. Some insulators can become conductors if you work hard. You can induce carriers in diamond, for example, and get some metallic or semiconducting transport on diamond, but in boron nitride hasn't happened yet. So boron nitride is as good an insulator as it comes, higher band gap than diamond. right? And well, diamond actually is not very high, but it's the highest known. I think there's no other material with band gap as high as that. So it's a good insulator, and because of that by itself, it's not very useful. And also because it's a good insulator, it acts very well to modify graphene band structure, but does not contribute its own carriers in any way. So it's only graphene that is affected.
What's the order of magnitude of the gap, the opening of the gap in graphene?
Signatures. Sorry,
the order of magnitude?
Oh, the order of magnitude. Yeah, it's right here. These experiments that I just described, they have been done in several groups over last 2 years, and what people see is that in this graphene and boron nitride structure with axis aligned or nearly aligned, you see a very strongly resistive behavior near the Dirac point, instead of metallic behavior that you see in graphene resistivity, where resistivity doesn't change, changes very little as a function of temperature. Here you see exponential increase of resistivity with temperature, and from this exponential increase, using activation model for transport, one can infer the band gap, and it is of that scale in all these different experiments. I mean, each of these experiments is a separate story, and I don't want to get too deep into it. There is an experiment in Stanford, in Manchester. Actually, the first time it was clearly observed was experiment at MIT, where they also saw side Dirac peaks due to superlattice effects that we'll discuss shortly. But in any case, in all these experiments, you see activation gap of order a few hundred Kelvin, which is pretty good. I mean, it's not it's not good enough for industry. Industry would like an electron volt gap, but it's good enough for physics, and we can do interesting physics with a gap which is that big. Yeah.
If we're trying to generate transform graphene into a topological insulator by if we deposit it onto boron nitride, the nature of the gap is due to the breaking of AB. It's like a staggered potential.
Yeah, so it won't be a topological insulator. Well, I aim lower than that, but I want to do something clean, and graphene will help. Yeah.
According to your spectrum, they have a symmetry in negative and positive bias.
Mm-hmm.
That means we also break the particle hole symmetry in our experiment, or it is just due to technical problem?
No, so that doesn't. Particle hole remains intact. Okay. Okay, so maybe, I don't want to get too deep into that, but let me say this. Even if you don't introduce the perturbation, even if you take graphene, particle hole symmetry in graphene is an approximate symmetry, because it would be exact if fermions would be non-interacting. But because Dirac Fermi C is filled with interacting particles, and so just that is enough to create particle hole asymmetry in graphene. The fact that you have charge in the Dirac Fermi C and no charge in the conduction band, that already breaks particle hole symmetry. However, these effects are weak. They may become stronger here. So I'm not aware of any experimental probe of particle hole asymmetry in graphene, even though theoretical grounds it should be there. You may be right that in this case it will become stronger and more accessible, but I'm not aware of any discussion of that. But it's a valid point. Right. So first thing I want to understand, it's very very simple exercise, and I don't want to spend much time on it, what kind of, what kind of Berry curvature distribution we get in the Bloch bands, and it turns out that the result depends slightly on the exact alignment of graphene and HBN lattice, and there are two cases that can be distinguished, both of which are realized in experiment. If you have graphene and HBN lattice aligned imperfectly, then you get a structure which is called Moiré pattern, and the periodicity of this Moiré pattern is about 150 carbon spacings, and that's because the HBN period and carbon period is about 2% mismatch. So there are about 15 nanometers. There's about 15 nanometers periodicity, and if you translate it into the band structure, you will see that each Dirac cone in the K and K prime point acquires side gaps because of Bragg scattering by that periodicity wave vector. And then the other case that is also observed in experiments is when you have perfect alignment. Then for perfect alignment, you get commensurate stacking. And what you see in the atomic force microscope, with the atomic force microscope, is a hexagonal domain pattern where in each hexagonal domain, again, periodicity is about 150 carbon spacings. In each hexagonal domain, the two lattices are in perfect register, and they form, AB, BA stacking of some kind. So it's the same stacking in all domains, and the strain due to mismatch of periodicity is relieved in the regions at the domain boundaries. Right. So these are two papers where these structures have been shown. Yeah.
Can you describe a bit more how the band structure changes?
Yeah. Next slide. We'll see that. What? There may be some interesting kinetics. I was wondering about that myself, but apparently it's very fresh, so maybe when people look more closely, they will see some variability, but so far, everyone says that they see this. So apparently it goes into that state quickly. Right. So the band structure change can be, you can understand it on different levels, but turns out that after you work hard, turns out that the simple model where you start with massless Dirac Hamiltonian for one valley and then just add a perturbation which is of the form of a mass term with position dependence, that is enough to explain all the key features. And you can add more terms into the picture, but that doesn't change the results. So there is an average value of mass that is responsible for opening the band gap, and then also there is spatial modulation due to mismatch in periodicity, and that produces Bragg scattering at some energy off the Dirac point in the conduction band and in the valence band, and you get these gaps opening up. And so the important thing here is that because the mismatch in periodicity is so small, it's only 2%, you can ignore inter-valley scattering. So you can focus on one Dirac point and work out the band structure near one Dirac point, and there will be some small patch in K-space, which will be the superlattice brilliant zone, which will be of size 100 times smaller than the main brilliant zone size, right? And so everything you can understand everything focusing on that and ignoring coupling between K and K prime points, which is small for such as slowly varying Bragg scattering perturbation. And so then you get these band structures. You can analyze Berry's curvature, very easy to do. What you see is interesting. Find that the Berry's curvature, positive red negative in blue. Well, A, it's concentrated near Dirac point and also near these side Dirac points where, at the high and low energy, where avoided crossings of these bands occur. And B, it's of different signs, so that if you take this Berry's curvature and integrate over superlattice brilliant zone, you get 0. And this is so because for that case you have opposite signs of this term and that term, and we can
The signs are reversed for the other term?
Yeah. So it follows. Yeah, exactly. So the important thing is the sign relation, and for the other case, the signs are equal, and so you get equal Berry's curvatures. Same arrangement, but equal sign, and so when you integrate that, you get a non-zero Chern number, which is plus for conduction band and minus for the other band. And so this is it. Basically, we have two types of structures, and we can, by changing angle, we can go from one to the other, and they have bands with different Chern classes. So, I mean, this is just to convince you that we have it on graphene, and now we have Berry's curvature, and it has an interesting distribution in the brilliant zone, and we can now take that and try to study an almost Hall effect. So that's the next part. Maybe there are some questions. Yeah.
So for zero angles, there is the Chern number equal to 0, I understand.
For more, yeah.
And it cannot be continuous transition when you start rotating.
That's right. There has to be a transition. So there is more there to study. If you try to align angles more and more carefully, at some point it should snap from a trivial state to a non-trivial state, and how that happens. Maybe there will be some spatial reorganization of some kind. Maybe something. It's not wide open. There's no single person who even tried to say anything about it. So wide open. Yeah.
Could you just comment a little bit on how you treat that in the second term? So the second term, which is mass variation, has some periodicity.
Mm-hmm.
And do you now solve the band structure within this smaller Brillant zone associated with this with a superstructure, or do you use some sort of local density approximation because X is varying slowly in space?
Yeah. So. So to get the numerical value, I mean, there is some mystery about the numerical value and where you get it from. We take the value. So there are Benicio calculations that study what happens if graphene and HBN are perfectly aligned and are in register. Then you get a small unit cell, and you can use a Benicio to do analysis, and then from that you get coupling, the modulation, which is of order 400. I mean, varies from paper to paper, say a few hundred Kelvin, right? Now, if you try to,
well, but the shift calculations, you shouldn't believe that below something like.
Of course, yeah, but I'm trying to use whatever evidence I got, even anything comes useful, right? So so you can. I mean, I have no expertise in ab initio calculation, so all I can do is look at these papers, compare what different papers say. They say roughly the same thing within a factor of 2 or 3, and that's I'm not sure what to make out of it. But let me tell you what happens if I go on and use these numbers. If I go on and use these numbers, then for more and calculate the size of that term. So there is a number in the literature for this value. And then if I use that and calculate this value, I find that it's too small about 2 orders of magnitude too small to explain the observations, and presumably something else is going on, and we have a paper trying to explain it using interaction effects, and again, probably there are other effects that may explain it. Maybe there is some deformation involved, and so the exact numbers are under discussion, right? However, I mean, for the start, ab initio papers give you a few hundred Kelvin, and that seems to be in agreement. So when next week when we'll talk about interaction effects, we'll come back to that. But I'm not going to talk about it today. Right. So yeah. So do Valley transport. So in graphene, as well as in many other materials, and atomically thin and in bulk 3D, we have valleys, and because Berry's curvature is of opposite sign in different valleys, and this is so because of time-Russell symmetry. I have no magnetic field applied, so Berry's curvature integrated over the entire Brillouin zone should give 0. And it may be non-zero in one valley individually, but it should be compensated by the valley. So Berry's curvature is non-zero, but adds up to 0 if I sum over the entire Brillouin zone. It's non-zero in one of the valleys. That's the case in graphene. Also the case in MOS2, which has band structure that looks very different, but from all the discussion we had about Berry's curvature, it's similar. So there is a Berry's curvature distribution at point K, which is positive here and negative here, and at K prime it will be negative here and positive here, etc. Then, of course, there are materials with valleys like silicon that don't have Berry's curvature, and so there is no anomalous Hall effect, and so we have to choose the one that has Berry's curvature and not to use the one that doesn't. Now, if we have Berry's curvature, we can have anomalous Hall type transport, and we can generate currents which are dissipationless, that flow perpendicular to electric field, and also these currents will flow in opposite directions in different valleys, and so that we want to see their effect. It can be done in a variety of ways, and maybe before showing our work, let me mention some efforts using optics. In the band gap materials like MOS2, one can try address states in different valleys individually using circular polarized light. And the reason this is possible, again, is related to Berry's curvature. If you think about selection rules for light absorption, you find that light of one circular polarization will be absorbed only in one valley, the other polarization absorbed only in the other valley. So using circular polarized light, one can pump carriers in each valley individually and address them selectively. And people have been doing it over the last few years in this material, and indeed you see that this individual coupling to light with different circular polarization works beautifully. And if you want details, ask me. There was even a very recent transport measurement. This is the paper on the archive in Paul McEwen's group, where they pumped circular polarized light and used the 4-probe geometry to measure Hall effects. So they applied electric field here and measured voltage here under pumping the circular polarized light, and they didn't see Hall effect in the absence of pumping, of course. Zero magnetic field, right? So that's one approach.
Sorry.
Yep.
Do you have the frequency scale for that? The order of the gap?
So the gap here is, you mean the band gap? The band gap here is MOS2. I think it's about. It's a EV scale. It's about. I think it's about 1.2 EV. So this material, again, it's very hard to gate it to induce carriers and measure transport, but one can do it optically because the band gap is in optical range, right?
I have a question.
Yeah.
I didn't understand why it's different circular polarizations, a couple different lengths of the values. I thought, a circular polarization is like angular momentum, so I
that's right.
But then here's linear.
Yeah. So one needs to work out optical selection rules for absorption, and so what you find is that if you take our Dirac Hamiltonian, which has the right symmetry to describe it, and calculate dipole matrix element between state here and the state here, you find that only dx plus I dy has non-zero overlap, and the one with a minus doesn't. And then in the other valley, it's the other way. Right. So what we are going to do is to use Berry's curvature to manipulate values. That was the original plan, and I showed previous U-graph just to explain what else is going on. We have these pockets with Berry's curvature, so we're going to use to tune carrier density to have Fermi level here or here, and then apply electric field and try to observe Hall current. Hall current, as we already said, will be charge neutral because it will flow in opposite directions in different valleys. So there is a valley Hall effect, as people call it. You get a charge neutral current flowing transverse to electric field, and there is a Hall coefficient, valley Hall coefficient describing that. Right, and so that's, reiterate again, you have it in systems with Berry's curvature and don't have it. If you don't have Berry's curvature, it's not enough to have many valleys. You need to have Berry's phase. Okay, so detection. To detect valley currents, what one can do is use a non-local geometry. Schematic is here. Suppose we have a long sample and we apply charge current over here, and then this charge current over here will create transverse current, which will flow in opposite directions in different valleys. This transverse current will tend to create imbalance between valley population. Particles in one valley will tend to flow in one direction, and the other valley in the other direction, and there will be so there will be an imbalance spreading along the system. What's important is that this imbalance is transmitted by a charge neutral current. Because of that, it can spread far away without charge building up and creating electric field that stops it from spreading. So because it's charge neutral, we expect to see a long range propagation, which is limited only by inter-valley scattering and valley degree of freedom relaxation. Right? No stray current effects. Right? And we'll come back to that in a moment. But that's an important point. Detection can be done at a remote location using the reverse effect, or reciprocal effect. Because if you have charge neutral valley current, it will create transverse electric voltage by the effect which is Onzaga dual or reciprocal to this one. And so you can use valley Hall effect both to induce valley current and to detect it at the remote location. And one way to think about it, maybe amusing, is compared with radio, where we have charge degrees of freedom that create electromagnetic waves, and then electromagnetic waves are charge neutral, and then they transmit information, energy, etc., and then they are detected on the other end again by some charge dynamics. Okay, so that's kind of what we're doing here, except that this is a zero frequency, so this is a DC measurement. There will be no oscillation involved. Right. So the experiment is done in a graphene device which looks like this, and it's prepared the way we described. So we place graphene and boron nitride, axis aligned, find a place where it's clean, and then carve out a long bar. So this length is about 10 micron with several side contacts, and then induce current, run current through one pair of contacts and measure voltage at a remote pair of contacts. And the reason this geometry is used is that we want to clearly separate from a trivial effect. Trivial effect would be simply straight charge current. If you, let's say, if you have a purely ohmic transport, and you run current this way, there will be always some current lines that will go out, and those current lines, there will be very small number, but those current lines in principle will produce some voltage drop, non-zero voltage drop, even at a remote location. However, one can, this is, of course, well known and well understood. The size of the effect will go down exponentially with the aspect ratio, and it's very well known formula called van der Poel bound for probe measurement. So the idea is to make sure that the aspect ratio is large enough so that this trivial effect is is off the table, and so that's what is observed in the experiment. The black curve is the longitudinal resistivity, meaning the voltage measured at the same pair of contacts as current, and then a red curve is the non-local signal. So you see, so first of all, you see that non-local signal has a much sharper, much steeper density dependence. It forms peaks which are much steeper than the local resistivity, and this is, it's significant in several ways. One is that it's another way to prove that we're not looking at some stray ohmic resistance, because if that was the case, then the signal will be proportional to rho xx, and clearly the red curve doesn't scale with density the same way as the black curve, so clearly a non-ohmic transport mechanism. Also, the positions of the peaks are exactly where we expect Berry's curvature to be present. So you should think about this axis as gating chemical potential through the band structure, and so in this region we're near the main Dirac point where we have pockets of Berry's curvature, and here we're near this side Dirac point, as people call it, where we have another pocket of Berry's curvature, and there should be a similar feature here, but it's not seen, and we don't know why. But as you can see, longitudinal resistivity is also asymmetric, so perhaps there is some scattering mechanism at these energies that suppresses resistivity, also suppresses non-local effect. So that's what is observed, and comparing to valley Hall response, can say two things. First of all, you see that valley Hall response when you calculate it peaks at the Dirac point, and that's how it looks. Also, Hall conductivity, maybe a little less intuitive, but Hall conductivity as a function of carrier density doesn't change sign when you change sign of polarity of carriers. Unlike ordinary Hall conductivity. Ordinary Hall conductivity, if you remember, is in a classical model it looks something like that. So this 1/n dependence means that as a function of carrier density it will go up here and will go down here. And this is classical. This is before quantum Hall effect sets in. And then in the quantum Hall regime you get some plateaus here. But point is, point is that there is the sign change, and then for this effect due to Berry's curvature, can look into it and show that there is no sign change, and so that's consistent. And yeah, and so then one can look further into it and ask what happens if you use different pairs of contacts, how this non-local signal decays as a function of distance. And so you can see that dependence on distance is exponential. It goes down exponentially with the characteristic length scale, which you can read of. This is log scale, this is linear scale, so you can see that it drops by a factor of e for distance over the micron, and 1 micron also happens to be the width of the strip. So it is possible that valley scattering only occurs when carriers scatter off the boundary, which is rough, and all microscopic structures is completely distorted. Maybe other inter-valley scattering mechanisms that we're not aware of, but at least this width comparison to width is suggestive that maybe main effect is at the boundary. So anyway, I think I should maybe wrap this up and switch to something else. And I can go on and on because this is what I've been doing recently. But anyway, so the main point is that there is a non-local response which is observed at B equals 0. There's no magnetic field applied, and it is clearly distinct from all trivial effects that you can think about, and agrees very well with Berry's curvature induced by gap opening.
What is the temperature of these experiments?
Yeah, so temperatures, I think it goes down when temperature is raised above 70 Kelvin or 50 Kelvin, and then the temperatures below that, it's roughly like what is shown. There is no strong temperature dependence at low temperature, again, in agreement with the fact that it's a pure metallic response of quasi-particles, which live according to their equations of motion. There's nothing many-body going on. Right. Yeah, so the range is 50 Kelvin or something like that. Right. Yeah, and so then, of course, experimentalists like to have knobs, so they added additional gate on top to see if they can gate this non-local response, and sure enough they can. So they put a small wire across the sample, and then they see that with voltage applied on that small wire, they can turn non-local signal on and off, and from electrical engineer point of view, the characteristic is fairly good. You have 2 orders of magnitude change over voltage change, which is only 20 millivolts. So it's comparable to what people like to have for applications, even though we're not claiming anything at this stage. Right. So let me spend maybe 30 seconds on that slide. So what we're thinking to do next is to use this technique to try to develop a more selective probe of Berry's curvature and measure its distribution in a band. In particular, what I've been showing so far is not sufficient to distinguish between trivial and non-trivial Chern class. The reason is that my signal, non-local signal, was proportional to Hall conductivity at the excitation point times Hall conductivity at the detection point. And if carrier density is uniform across the system, it will be proportional to square of Hall conductivity. So I won't see the sign change that tells me that there is a non-trivial Chern number. And in order to see the sign change, what needs to be done is, for example, a split gate geometry where we tune carrier density individually in different parts in different parts of the sample, and hopefully this boundary is sufficiently smooth to get Valley current across, and then we'll be able to do a full Berry's curvature spectroscopy, sign included, and that will give access to chair number, right? And then there are various other ideas. Can ask me later. Yeah. Any question? I mean, people are going in sleepy mode. Yeah. So maybe I should change subject. Okay. Let me skip this. Right. So. So good. So the next topic I would like to discuss is going back to basics. Actually, going back to what we worked on 5 years ago. I mean, I picked the recent topic because it was kind of in tune with the rest of the school program. Also because I'm selfish and nice to talk about what you're thinking right now. But anyway, so if I want to explore relativistic quantum mechanics and graphene, then we should start with basics and ask about how we can show experimentally that carriers in graphene respond to external fields, and compare it to what we expect from relativistic picture. And there is quite many interesting phenomena here that people studied, and I will try to describe it quickly. Right. So this is a quick reminder about Diracness of graphene spectrum. This is atomic structure. This is the full Bloch band structure. This is this picture of Darth Vader mask that I was trying to armor, that I was trying to show yesterday. And then if you linearize near these points, you get massless Dirac dispersion relation. If you add slowly varying external potential, slowly varying compared to carbon spacing, so any reasonable potential induced by gates or by external fields will be like that. Then you get Dirac equation in external fields, scalar potential and magnetic vector potential, and you can ask how can we see that it's Dirac equation? The simplest experiment to do is to look at the Landau levels, and this is done by transport measurements measuring magnetic oscillations or quantum Hall effect. And what you see is that Landau levels behave, or you can do it optically also, and that also has been done. So you can see from all these measurements is that Landau levels behave exactly as you expect from a massless Dirac Hamiltonian with magnetic field added into it, as we did on the previous page. In particular, Landau level spacings scale as a square root of magnetic field, and they are arranged in a particle-Hall symmetric fashion. And there is a zero mode. There is a Landau level at zero energy, and otherwise they're pairwise distributed energy plus En and minus En, and these energies scale like that as a function of Landau level number and as a function of magnetic field. And so this type of scaling is very different from what we get for quadratic dispersion relation, like say in the semiconductor. It's related directly to Diracness. For quadratic dispersion relation, we get Landau level spacing which is proportional to magnetic field, Larmor frequency, and here it's square root of B. And because of the square root of B, Landau level spacing in graphene is much higher than in any other material known. In particular, it can be as large as 10,000 Kelvin for magnetic field of size of 10 Tesla, and so it means that even at temperature as high as room temperature, you can get Landau level fully occupied and the level above it fully empty, and so you expect to see quantum Hall effect even at room temperature, which is what indeed is observed. To remind you quickly why Landau levels behave like that, let me just show these two equations. So Dirac-Hamiltonian can be obtained as a square root of Pauli-Schrödinger Hamiltonian. That's basically how Dirac originally arrived to his Hamiltonian. And in 2 + 1 dimension, it's enough to use 2 by 2 Pauli matrices. If you go to 3 dimensions, you need to double size of matrices, but in 2 dimensions, 2 by 2 is enough. So you can take a square root of Pauli-Schrödinger Hamiltonian to get Dirac-Hamiltonian, and then you can use that, or you can do it in the opposite way and take Pauli-Schrödinger Hamiltonian and factor it and write it as a square of Dirac-Hamiltonian. And then we know Landau levels for Pauli-Schrödinger Hamiltonian. They're just spaced by cyclotron energy EB divided by mass, and so we can take and they're proportional to a Landau level number, form linear sequence. If we take a square root of that, we get the answer for Dirac-Hamiltonian. Right, and when you do transport measurement, you see this pattern very clearly. You see that there is a Landau level sitting exactly at 0 energy, and then pairwise symmetric Landau levels sitting at positive and negative energies, and in between you have quantum Hall state, quantum Hall plateaus, and yeah. Okay, right. So yeah, and it survives up to room temperature. Also, what you observe is that the values of filling at which Landau level, at which the quantum Hall effect is observed, is half integer as compared to what you expect based on integer Landau level occupation. And so this is known as half integer quantum Hall effect. If you, different ways to understand it, but one way that I would like to mention, because we talked about Berry's phase, is related to thinking how Berry's phase, which is pi for the Dirac point, changes the Aharonov-Bohm quantization that we usually use to explain Landau level quantization. So if you take a normal material, no Berry's phase, to get Landau levels from a quasi-classical picture, you have to do the following. You have to take cycling orbits, and quasi-classically classically they exist for any energy and for any orbit radius, and then you have to demand that the closed orbit encloses an integer multiple of flux quantum, and that gives quantization of orbit radius and also quantization of energy that gives the Landau quasi-classical expression for Landau levels, which happens to be also an exact expression for Pauli-Schrödinger Hamiltonian. If you want to do it for massless Dirac particles, then you have to add one more ingredient. You have to remember that for massless Dirac particle there is velocity pseudo-spin locking, and so when particle goes over an orbit, its velocity is doing this, and that means that spin, pseudo-spin, which is also locked to velocity, is also doing this, and that type of dynamics gives Berry's phase pi, which should be included in that phase, and then after you do that, you get a condition which is different from that. You get a half integer rather than integer multiples of flux quanta that can be enclosed. And from that you can predict that there will be a half period shift of Shubnikov-Dehaas oscillations as compared to the normal case, right? And so that's indeed what is observed. Okay, so that's this is how graphene was first, carriers in graphene were first recognized, that having to do with relativistic particles. Okay, any questions on that? That I think well known. I try to do it quickly. All right. Good. So, Klein tunneling. So, Klein tunneling is another quantum relativistic phenomenon. Basically, as soon as the Dirac equation was introduced, Klein tried to solve the problem for Dirac electron impinging on a potential barrier, and he discovered that higher the energy, the easier is for the particle to get through, and we can, understand it very easily, because if we take the Hamiltonian that we, sorry, where's my, yeah.
Do you know of any other reasons why you might get a half integer?
Other explanations, yeah. So there are lots of explanations in the literature. You can work it out using H states and show that H states are organized in such a way that you get half integer behavior. You can work it out. Let's see. There is a third explanation that I.
Sharing of vacuum state with particle.
Yeah, there's also an explanation that was proposed maybe 20 years ago before that came out, based on parity anomaly by Roman Zhakiv. So you can find this half integer effect in his paper. You can maybe talk about it next time. Right? And then, sorry, you said.
An explanation about sharing the vacuum state with the particle and hole.
Uh-huh.
So only half of the conductance is taken into account for the transport. It's proved to be equivalent to the sublimation of the Dirac curvature. I remember they are about the same time to be.
Can you say a bit more? I'm trying to picture it.
When you solve the Hamiltonian, you can see the vacuum state is both the ground state of the particle state and hole state.
Mm-hmm.
So if the entire vacuum state contributes 1 unit of quantum conductance, then it's shared by particle and hole. So you can only take half into account. It's one of the explanations proposed by Guyton.
Okay, so actually that sounds a bit like Zhakiv story, but he formulated for Landau level occupation, you are saying for currents. So, yeah, so maybe by some kind of Lorentz transformation one can go from density to current. Yeah. Right. Yeah. Okay. Klein tunneling. All right. So, right. So Klein tunneling is, it was considered in quantum electrodynamics as something very fundamental, but also somewhat of a curiosity, because people never could think of good ways to probe anything like that with real electrons. In graphene, however, it's our everyday life. And you always have to think in a variety of settings. You have to think about massless particle going through potential barrier. And if you solve this problem, you find that because of chirality, because of velocity and pseudospin being locked together, you have absolutely no backscattering when particle is normally incident on the barrier, and can give a general proof, or you can just solve an example, let's say rectangular barrier, and then for rectangular barrier, transmission as a function of incidence angle will be unity regardless of the barrier specifics, width, etc. It will be unity in the normal direction, and then it will have some other funny dependence in other directions. Okay, and so the question is, and it's related to Klein tunneling because graphene is a ultra relativistic case when mass is zero, or what you get for massive Dirac electron in a limit of high energy, right? So one can, it's an interesting behavior. It means that you can't create barrier that traps create a corral that traps Dirac electron. You can use this for Schrödinger electron, put it in, and it doesn't escape. But if it's a Dirac electron, at normal incidence, it can always come out, no matter how high the barrier, right? So the question is, can we demonstrate it? And very soon after graphene was introduced, people proposed that we should be able to see it from conductance measurements, because conductance is basically a transmission that you have to sum over all transmission channels. There are caveats, and one has to think carefully how we do it, because well, first of all, there are many channels, and you want to show a clean measurement that preferentially probes normal incidence. Also, when you do transport measurement, you always plague to some extent, even though graphene is a highly ballistic material. You get ballistic mean free paths which are enormous compared to other materials. You always get some contact resistance. So if you want to show that it's perfectly transmitting, it's not possible, because there is always some imperfection because of contacts here and there, and resistivity added to it. So you can't show that it's E square over H conductance or something like that. That simply doesn't work. So people looked for other ways, and one such way is what I'm going to talk about here. So this is a proposal based on the following idea. Let's, rather than trying to think about transmission, let's try to think about reflection. And so Klein calculation tells us that that reflection vanishes for normal incidence, and that also means that if you take reflection amplitude as a function of the angle, it will go through zero as a function of the angle. And supposedly it will be some nice smooth function of incidence angle. And if you have a function of some parameter that goes through zero, it changes sign, right? Changing sign you can interpret as a pi jump in backscattering phase. So again, maybe I said it too fast, but if you think about reflection in the Klein regime will be exactly zero for normal incidence and slightly non-zero for other angles. And then if you vary angle, it should change sign, and that means that there will be a pi phase difference between trajectories coming at small positive angle, trajectory coming at small negative angle. And so one can ask, can you detect this pi phase in some kind of Fabry-Perot type interference geometry? And turns out that it's possible, but one needs to introduce an additional knob to be able to vary the angle and trajectories that contribute in a dominant way. And it turns out that a very convenient way to do it is to introduce a weak magnetic field. If you introduce a weak magnetic field, what happens pictorially is shown in this picture. So at zero magnetic field, you have trajectories which are, let's say, in some approximation of straight lines, and then you get an angle here and an angle here, and you can show that the phase jumps associated with these angles cancel. But then when you introduce a weak magnetic field, then you get different kind of trajectories, and they are reflected at angles which are of the other sign, and so their contributions to phases don't cancel. And so based on this idea, you can set out to ask how the phase in the Fabry-Perot interference pattern changes as a function of magnetic field. And sure enough, you find interference that shifts in phase by pi when you apply a small magnetic field. So what's shown here is is some barrier. Doesn't matter what shape. So I think it was done for a parabolic barrier, but it doesn't matter. And then for b equals 0, transmission as a function of incidence angle, which is parameterized by parallel component of momentum, and as a function of energy, shows a pattern of Fabry-Pérot oscillations. And then if you apply a weak magnetic field, you see that there appears a line of nodes, and then crossing this line of nodes, you see a half a period shift of the pattern above compared to the pattern below, right? And so you can say that this was only for, selective for different values of momentum. What will it do for, if you measure total resistivity, which will be conductance summed over all trajectories? Luckily, phenomenon survives, and if you take resistivity as a function of energy, you see that at low magnetic field there is a periodic pattern, and going to high magnetic field, it shifts roughly by half a period, going over some critical field. And so that's the proposal that, if we see that, we know that there is a pi phase jump for backscattering, and pi phase jump also means that a reasonable function must go through 0. So it will also demonstrate that Klein probability of Klein tunneling is 1 in the forward direction. And so this experiment was done actually as we worked on that idea. It has been done by in Columbia by Philip Kim, who will be here and perhaps maybe talk about that also. And so what they see, this is an old slide, very poor quality. I apologize for that. But basically, what they did is that they took a graphene ribbon and put a thin wire on top to create potential barrier, and then measured, and they saw Fabry-Pérot oscillations for particles that go through this system, and as a function of magnetic field, they saw some pattern, and if you look closely, there are kinks which are about half a period. If you zoom in, you see it more clearly. There is some periodic pattern, and then here there is some kink, and that's the thing. These are not Landau levels. Landau levels are a fan which you see here, and for carriers for one polarity, and on the other side for carriers of the other polarity. And interestingly, they placed this panel so that it's hiding something, and I'll tell you in 5 minutes what's behind it, right? Anyway, so that's an experiment, and that shows phase jumps, and let me see what else is interesting. One can do similar analysis, and actually it's much even simpler, for an important case when Dirac electron is moving in a constant electric field. So that models, it models a situation when you have some potential step. Let's say you have carriers of one polarity on one side, carriers of other polarity on the other side. You create a step in carrier density by using a split gate geometry. So there is some density step like this, and in the middle region, the potential that electron C can be approximated by constant field. And this is a problem which is interesting to solve, also very easy to solve, because you can use WKB approximation and find tunneling probability for tunneling through classically forbidden region using simple WKB formula, and then by some magic turns out that it agrees with the exact solution, and we can talk about it a little later. So that exact solution, or this WKB formula, exhibits the same type of behavior. You have full transmission at normal incidence and a reflection at other angles, some reflection at other angles, and by tuning this field, you can make the collimation effect. You can enhance collimation effect. There'll be strong collimation in the forward direction, and for angles which deviate from that, there'll be a nearly there'll be a strong reflection, nearly perfect reflection. So there is this collimation phenomenon that I think is very interesting, has not yet been explored experimentally, but surely will come out somehow. Right. So that's the story about p-n junctions, and we'll see more of that. Now let me not talk about that. So this is how the same result can be obtained using exact solution by mapping this problem on another classical problem, which is called Landau-Zener transition problem. Maybe we'll talk about it next time. And now let me talk about something else. So related to that, p-n junction modeled by constant electric field, one can ask whether something interesting happens if we apply a weak magnetic field in addition to electric field. And so this I think is really interesting because it probes the Lorentz invariance of the system. So if you take relativistic motion in classical electric and magnetic fields, then in classical E&M we know that there are two regimes. Depending on whether electric field or magnetic field is bigger, we can find a moving frame, and in that frame it will be a pure electric or a pure magnetic field. And we can eliminate one of the fields by going to a moving frame. And so there are two cases for relativistic motion in classical E&M. And that survives in the quantum problem as well. And you get, the classical dynamics is like that. You get in the electric case, electric field is much stronger than magnetic field. You get open trajectories which are, parabolic type, and more precisely what they are we'll see in a moment. In the case when magnetic field is stronger than electric field, we have cyclic orbits drifting perpendicular to electric field, and that's something that may generate quantum Hall behavior if we go to the quantum problem. So the question is, can we understand these two regimes in the graphene p-n junction? And so to do that, one way is to just use the same approach, going to moving frame, doing Lorentz boost, going to the moving frame, and it can be done by rewriting, rewriting 2 plus 1 dimensional Dirac equation in a Lorentz invariant form, introducing 3-dimensional space-time coordinates in the usual way, and then multiplying Dirac-Schrödinger equation by suitable Pauli matrix to bring them to the form where they form gamma matrices obeying the standard anti-commutation relation, right? And so if you do that, your problem becomes Lorentz invariant, and you can apply the same argument with Lorentz boost to the quantum problem and see that there are two regimes that where you expect to see a very different behavior. So in one case, where you have open orbits, you expect to see a full transmission. You expect to see a transmission through your potential, and in the other case, where you have cyclone orbits drifting, there will be no transmission. So in one case there will be finite conductance, in the other case there will be zero conductance, and transmission from one to the other, transition from one to the other, and so it's very much parallel to the classical E&M case. The only difference is that here we have Dirac-Fermi velocity instead of the speed of light, and so when you work out these invariants, there will be v square here, but c square here, or maybe the other way around. And so there will be this factor, proportionality factor, in the relation between magnetic and electric field, giving the boundary between magnetic and electric regimes. Yep.
The gamma matrices here are 2 by 2? Or?
2 by 2, yeah. It's a 2 plus 1 Dirac equation, so we can do everything with 2 by 2 matrices.
But if we're going to talk about boosts, and we have the extra dimension of time, the boosts will affect the time
That's right. So it's a 2 plus 1 Dirac equation. And we can handle that with 2 by 2 matrices. If it would be a 3 plus 1, then we would have 4 by 4 matrices. Right. So we can do calculation using Lorentz boost. Let's say if I want to find transmission and how it depends on magnetic field, the easiest thing I can do is to go to the frame. In the electric case, I can go to the frame where magnetic field is 0, and then find transmission there. And it's easy to argue that transmission coefficient is Lorentz invariant, because transmission coefficient simply determines the probability to come from one side and pass on the other side, and that's invariant no matter what moving frame you're viewing it and so you can find transmission in the moving frame and then transform it, do Lorentz boost to transform it back to the lab frame and get full dependence on magnetic field. And then if you use that transmission magnetic field dependence and the transmission to calculate conductance by summing over all transmitting channels, you find some magnetic field dependence which is of this form. Conductance is suppressed by magnetic field and becomes 0 when magnetic field reaches the critical value. And for realistic parameters, you can estimate that this critical value will be a few Tesla. And people did measurement of this type and found something similar. I mean, geometry they used wasn't a step; it was a barrier. So there were 2 steps, some differences, but overall you see that qualitative behavior in the Stanford experiment. Okay, so yeah, you can also use magnetic field to control the collimation angle, but that's maybe not so interesting. What is interesting? Let me mention this and maybe stop here. Or show one more slide. So what is interesting is that you can also understand that if you're uncomfortable with Lorentz transformations done in this artificial way, and you want to avoid Lorentz transformations, which they're not genuine here. There's some trick, and if you want to do it without any trick, you can obtain the same results without Lorentz transformations. You have to work. You have to work a bit more. So you can start with, maybe let me leave it as a homework exercise. I mean, the key steps are here. But if you start with classical trajectory for particle with some dispersion, you can show using quantization of momentum components, etc. You can show that the trajectories take a very simple form in momentum space. And in particular for dispersion relation, which is massless Dirac dispersion relation, in momentum space you get trajectories that are described by this expression in polar coordinates, and that is very easy to identify with Kepler's planetary orbits. And depending on whether the eccentricity parameter, which is the ratio of this to that, is smaller than 1 or larger than 1, you get elliptic orbits, which corresponds to closed orbits, which corresponds to the B case, or open orbits, which are hyperbolas corresponding to drift velocity being larger than V. So that's an easy way to see this critical field value without thinking about Lorentz transformations. Okay, but so sorry for being rushed here. It's not a new result. We already obtained it on the previous few graphs, and I will be happy to answer questions. More important is to show what they were hiding in that experimental panel that I already showed you. If you now look at the full picture, you see that indeed Landau levels appear only when field is above some critical value, and there is a continuum spectrum. So this is field going from minus 8 Tesla to plus 8 Tesla, and this is gate voltage that controls carrier density somehow. And So let me maybe explain what we see here. We see Landau levels on this side, and Fabry-Perot and continuum states here, and then on the other side we have opposite polarity regions inside Fabry-Perot interferometer and outside, and so here we see these Fabry-Perot oscillations, and you can see even more clearly than before these pi phase shifts, that signature of Klein tunneling. You see that here in the middle it goes boom, 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 and above it there is some kink, and it goes approximately with a half period shift, right? And so we already understand that, but then on the side where polarities are equal and there is no Fabry-Perot interference, we see Landau levels, and Landau levels in this geometry, in the presence of constant electric field, appear only when magnetic field exceeds some critical value, and that's this critical field that we just derived, and one can do calculation, and sure enough you get a very similar value from that analysis. All right, so I think that's a short survey of quantum relativistic behavior in graphene. The last topic I want to talk about is Unruh effect, but let me leave it for next time, because I think we need to be fresh for that. Yeah. All right. So we're done.